Hi, welcome back to this course on computational thermodynamics and kinetics of materials. In this class, we will see how to apply CalFAD with effects of surfaces and interfaces. That is called nano CalFAD. We will see about that. Then we will see how to apply CalFAD for electrochemistry and also for process metallurgy. We will introduce some of those ideas. Okay, these are going to be the contents. Size effects, in the sense they are called as nano CalFAD, including basically the surface energy aspects into CalFAD. And we will also see how the phase diagrams change using a case study if we include the surface energy aspects. Then a related idea is how kinetics changes if surfaces are included. So we know that surfaces, grain boundaries are faster diffusion paths. We'll bring that into picture and understand how kinetics changes and how it is incorporated in the tools. Then we will see the electrochemistry and process metallurgy part, how CalFAD is used for that. This nano CalFAD, including size effects in thermodynamics, is basically applying CalFAD concepts to nano-sized materials, nanoparticles, thin films, nanocrystalline phases, nanoprecipitates inside a matrix of a bigger size. All these things have something extra compared to the normal thermodynamics that you have been focusing on, that is the surface effects. Okay, so when we go to these sizes, we get these size effects that are included because thermodynamics at nanoscale differs from bulk. We'll see how to do that. When we talk about materials with nano size, to bring in this size effect into Gibbs energy, we need to have bulk Gibbs energy plus surface Gibbs energy. Two things should be added. We have been dealing only with bulk for most of the class. So let's think about how to bring this surface energy aspect. Okay. So Gibbs energy of the phase, this is basically the phase which has the nano grains in that, let's say, is equal to G of the phase in bulk plus G of the phase, the surface Gibbs energy. Okay. In one of the previous classes, we talked about gamma being the surface energy, and if this is assumed constant, we can proceed with some of the treatments for this, how to get this G phase surface. This is basically Gibbs energy per unit area of material in the surface. This gamma is the Gibbs energy per unit area, right? Its surface energy is basically that. What we need is surface energy per mole, because this is Gibbs energy per unit area, right? So we need here Gibbs energy of a phase. This is usually in joule per mole. Okay, so we need this. We already have this in joule per mole. We need this also in the same sense, Gibbs energy per mole, the surface Gibbs energy. So, so to understand that, we can ask the question of, if some material is added to the surface, how much will be the change in the surface energy per mole? Okay, so if a material is added in the surface, then the area increases. Then G of phase surface, this is basically what is the change in the gamma provided the area increases with the addition of material. So gamma multiplied by the rate of area increment with respect to the material added. This n is the number of moles of material added and A is the area. If we keep a spherical geometry, we can keep the area capital A is 4 pi r square and volume is 4 by 3 pi r cube. Then we can calculate what are the number of moles, which is the total volume by volume of material per mole, that is molar volume. Okay, if we do that, we get the number of moles of atoms. Then dA by dN is dA is differentiation of 4 pi r square, we get 8 pi r, and dN, which is basically V by Vm, and if we bring V as 4 by 3 pi r cube, differentiate that and put it here, we will get 12 by 3 pi r square, and Vm is also there in the denominator. So if we rearrange this, we will get 2 Vm by r. So if we substitute this into this equation, gamma dA by dN, we are going to get 2 gamma Vm by r as the surface Gibbs energy. So this is a very important expression, because this is what we have to include here and add it to the bulk Gibbs energy. We have all the databases, Gibbs energy databases with us. We have to add this to that, but this has to be suitably modeled and added. The composition dependency and temperature dependency, those things are to be done for this, and then added to the bulk Gibbs energy that we already have in our databases. So in that way, the database becomes usable for nano-sized materials. This equation is what we got, but there are variations to this. Kapte in 2012 has expressed some problems with this and gave a new equation where 3 gamma Vm by R is used, and if this geometry changes or the uncertainty is there in the measurements of the surface energy, or if there are surface strains, okay, or the shape changes from the spherical, we need to have a correction factor, that is this C, that can also be included, so that this equation is more versatile for different kind of shapes and sizes of nanomaterials. And this gamma is what we have used in the class, in previous classes also, for surface energy. But in most of the treatments of this nano calfat, surface tension sigma is used instead of surface energy gamma. So this is going to be the expression used for nano calfat, and this sigma is modeled to have temperature and composition dependencies, just like the bulk Gibbs energy. An important note here, this sigma need not be constant. It's a function of curvature and segregation of elements. Okay, even at a single temperature and composition, this sigma need not be constant. Okay? If the curvature of the particle changes, the packing of atoms may change, therefore sigma can change. Also, certain elements may preferably sit in the grain boundaries or interfaces. They may also alter the grain boundary energy. Right. If at all this is correctly modeled, temperature and composition dependencies for this sigma and included in this equation and then brought into this Gibbs energy expression in the database, then the entire phase diagram will change, because we have been plotting it only using the bulk Gibbs energy till now. How it can change for nanomaterials is going to depend on the size of the material, size of the nano size of the grains, let's say. That is the one which is going to decide this. So that is usually considered as an independent variable. So separate phase diagrams are drawn depending on what is the size of grains. For example, this is a case study. Bismuth tin phase diagram modified for 10 nanometer sized grains. Okay. You can see the solid lines here are the bulk phase diagram, and when the grain size goes to 10 nanometer, the phase diagram changes significantly. So you can see melting point gets lowered in almost all the compositions. The eutectic reaction here, the temperature of that changes, the composition of that changes. So a lot of changes are happening because of this new thermodynamics, that is the size effect. Right. How about this surface tension in thermocalc software? In thermocalc software, this is there as a property modeled using modified Guggenheim model or the Redlich-Christer-Maggiano subregular solution model. More details are there in documentation set, you may explore. And that's about the nano calfat. Let's look at kinetics with faster diffusion paths. How is it incorporated? What we have seen till now is the mobility. The mobility that we treated is all about movement of atoms through the lattice. Okay, we can call it bulk. So mobility bulk is equal to m0 bulk exponential q bulk by RT. You know what are these terms. This is the frequency factor term, this is the activation energy term. But if you could recall, we also told this one, diffusivity is through surface, grain boundary and dislocation pipe are faster compared to the lattice diffusion. Okay. So this is the hierarchy. Surface diffusion is faster, grain boundary diffusion is slower than that, dislocation pipe diffusion is slower than that, then comes lattice diffusion, which is the slowest of all. So if material go to nano grains, these grain boundary contributions become significant, and if there are more dislocations, dislocation density is high, then again there is more diffusion. So these things should be carefully treated. We cannot simply use the lattice diffusion mobility. Okay. So in thermocalc, this grain boundary and dislocation contributions are handled in a very simple sense, that is basically go and change this Q. Okay, this Q is the activation energy. It is quite high, let's say, in the lattice diffusion, and that's why mobility in the lattice is slower. Okay, in the dislocation pipe or grain boundary, it is going to be faster. It means that activation energy is lower there. Okay, so what is done is simply a fraction is multiplied with this Q bulk. Let's see how it is. Okay, mobility through grain boundary is m0 bulk multiplied by exponential f red for reduction, GB. Okay, F red GB Q bulk divided by RT. So this F red GB is the fraction that we are talking about. Okay, bulk diffusion activation energy multiplier. So this is basically a fraction, typically 0.5. So half of the original activation is considered usually, and this can be modified by the user. Similarly, the mobility through dislocation is also multiplied by F red dislocation, which is again bulk activation energy multiplier for dislocation pipe diffusion, which has typical values of 0.8. Okay, you can see higher number is multiplied in case of dislocation, because diffusion through dislocation is slower compared to this, therefore activation energy will be higher. That's the reason, right? So then the weighted mobility comes, which is basically putting these things together in one single equation. Before looking at the equation, first let's understand these things. Delta is grain boundary thickness, which tells you the grain boundaries are not just a single layer of atoms. There is a thickness to that. It means more number of atoms can come into picture in grain boundary. Therefore, more disordered atoms and higher the contribution of grain boundaries. And D is grain size as a function of time and temperature. Smaller the grain size, higher will be the contribution of grain boundary diffusion. Okay, and then rho is dislocation density as a function of time and temperature. So if rho is high, the dislocation pipe diffusion contribution will be high. Then Burgess vector, this is the distortion created by a dislocation. If this is more, again the contribution of dislocation pipe diffusion will be more. So this is how they are put together. Delta by D mgb, this is grain boundary contribution, plus rho b square m dislocation, this is the dislocation pipe contribution. And this term is basically taking the m bulk and multiplying it with a fraction 1 minus something. Therefore, you are going to get a fraction of m bulk. This is done because the entire material is not bulk. The material is not only having atom sitting in a perfect lattice, because some of the materials are in the dislocation, some of the material is in the grain boundary. So those materials are to be subtracted from the total material, total lattice material. Okay, so that is what is done here. 1 minus the removing the grain boundary part and removing the dislocation part. So that's how you get the new mobility. So as a user, you can play around with these numbers if you know more about your system, and do kinetic simulations accordingly. Right, that's about kinetics in faster diffusion paths. Electrochemical properties, their application of CalFAT is for electrochemistry. Basically what we mean here is for electrochemical reactions, CalFAT can be applied. For example, corrosion in aqueous environments, which is a very big concern for the materials application. In addressing that, CalFAT can help. What we need to know is this: pH and electrode potential values of the aqueous solution phase are involved in doing this CalFAT for electrochemistry. And pour by diagram is a useful tool for this. It's like a phase diagram that shows the stability boundaries for a metal aqueous interaction system. The regions in this are like this. The immunity region is where no metal dissolution takes place, no corrosion there. The corrosion region is where active metal dissolution takes place, and the passivation region where a protective film forms, and this does not allow any further corrosion to happen. So identifying these regions in a diagram would be really useful, and CalFAT, especially in ThermoCalc software, there is a module called pour by module which is useful for that. CalFAT is also applied in process metallurgy. This is for reactions that occur in metallurgical processes. For example, steel making and steel refining processes, where reactions between liquid steels and slags and gases and solid oxides happen. In this we have two things, that is equilibrium simulation, where the thermodynamics of these reactions are handled, and process simulation where reaction kinetics is involved. This thermodynamics is applied for reactions of these different things, rather than for the transformations that we focused mostly in this particular course. The tools to do that is ThermoCalc process metallurgy module, and more importantly FactSage. This software is more customized for handling this reaction thermodynamics. Right. Thank you. I hope the lecture is useful. See you in the next class.